Welcome to video 3.2b for a discussion of the chemical properties of period 3, along with a look at the alkali metals and the halogens. And you'll have to understand that some of this video doesn't relate to acids and bases, but some does quite well. And so just follow along and join me for the ride. Gotta love chemistry jokes. In terms of your prior knowledge, certainly the periodic table and remembering period 3 and what that looks like, the third period. This is from sodium to magnesium to aluminum all the way over to argon. I was about to write neon, all the way over to argon. That's period 3. Certainly trends in the periodic table will be important, and of course acids and bases. It says here, I know that's not necessarily prior knowledge because we're really just beginning this acids and bases unit, but certainly I think you know enough to move forward with this video. The big idea: elements show trends in their physical and chemical properties across periods and down groups. Here are some syllabus statements related to our work on group 1 and group 17, the alkali metals and the halogens. So let's take a look. Alkali metals, group 1, are very silver, kind of silver colored, very reactive, and they're not found in their elemental form in nature. I have some sodium and potassium in my storeroom, and they're stored under oil to prevent contact with air and water. And they form 1+ ions, very low ionization energies relative to other elements, and the reactivity increases down the group. So why is that the case? Well, as you go down the group, the ionization energy decreases, and that leads to a higher reactivity because these elements, these metals, react by losing an electron. They're good conductors of electricity and heat because they're metallic, very typical of a metal. Relatively low densities, especially compared to other metals. And the gray shiny surface, when you freshly cut them with a knife, it actually starts to react with the air and oxidize. Remind me sometime to show you sodium and water. Now, right before IB exams. Very reactive metals, and they form ionic compounds with nonmetals. So here's a picture of lithium, sodium, and potassium, and I will certainly show you a reaction of sodium with water when we get near IB exams. Examples: when an alkali metal reacts with water, it produces hydrogen gas, which is flammable, which makes it kind of exciting. Remember that this potassium hydroxide will ionize into the potassium ions and the hydroxide ions when it dissolves in water. If you'd like to see a little bit more detail of these reactions, I recommend going to Compound Chem and doing a search for sodium and potassium reacting with water. See if you can find these pictures in his article, his infographic about the reactions. The halogens are group 17, and they exist as diatomic molecules. So chlorine gas, for example, is Cl2. It is a single bond between the two chlorines, and X is a common abbreviation for halogens as a generic look. Halogens: fluorine, chlorine, bromine, and iodine. And then astatine is below those, and we kind of ignore it because it's so rare. Less than a mole of it probably exists on the entire Earth right now. Melting point and boiling point increase down the group. Why? Because the molecules increase in size and the number of electrons, which increases the van der Waals forces for the intermolecular forces. Reactivity decreases down the group because as you move down the group, the electron affinity decreases, and that makes them less likely to gain electrons. When fluorine reacts with sodium metal to make sodium fluoride, the fluorine gains electrons, and this is something we'll study in topic 9. And as you go down the group, iodine is less likely to want to gain that electron, and so they become less reactive. Here's a look at iodine, bromine, and chlorine. Bromine is a very volatile liquid at room temperature. You can see some of the bromine vapor. Iodine's a solid, chlorine is a gas. That do tend to have color, and bromine is kind of brownish color. Iodine, again, is that kind of purplish color. They are quite reactive as nonmetals. They form ionic compounds with metals and covalent compounds with other nonmetals. Now, sodium reacts with chlorine to form sodium chloride. And so this is pretty common. In terms of reactivity, sodium very reactive, chlorine very reactive. If you just look on YouTube for videos of sodium reacting with chlorine, it's quite spectacular. Halogens can also exhibit displacement reactions, where the more reactive halogen will displace or replace the less reactive halogen. And the bromine ends up alone, if you will, or by itself. So as an ionic equation, the potassium exists on both sides. And so we have the bromide and the chlorine reacting and basically switching places, and now we have chloride and bromine. So in terms of predicting products for the following reactions, well, chlorine, if we look at the periodic table, FCl, Br, and I, increasing reactivity as you go up. So chlorine can replace iodine, and so we will get 2 chlorides plus I2. But chlorine cannot replace fluoride because fluoride is more reactive. So this is no reaction. The more reactive element ends up or stays in ionic form. So that means that this is no reaction. So chloride cannot replace fluorine. Chlorine cannot replace fluoride, but chlorine can replace iodide. This is a look at a silver halide, silver 1 chloride, or silver chloride, more commonly called. Here it's a white precipitate when it's made. Silver bromide, silver iodide turns a little bit more of a yellow color. These are insoluble, relatively insoluble in water. Now we're going to shift our focus to acids and bases and period 3. Oxides, so sodium oxide, magnesium oxide, aluminum oxide, and so on, change from basic through amphoteric to acidic across a period. Now, as we move from sodium to aluminum, these are all ionic structures, and we're talking about the oxides now. So again, we're still talking about sodium oxide and so on. These are ionic because the electronegativity difference between oxygen at 3.4 and these metals is quite large. Silicon dioxide, SiO2, is a giant covalent structure, and we studied that within topic 4. Phosphorus to chlorine, these are non-metal oxides, and they form molecular compounds or covalent structures. They form molecules. So here's a look at some formulas. Let's look at sodium oxide, magnesium oxide, aluminum oxide, silicon dioxide. Phosphorus makes a couple different oxides, sulfur makes a couple different oxides, and chlorine makes a couple different oxides, and we're ignoring argon. Electrical conductivity moves from high to low to none. The structure moves from ionic to molecular covalent with silicon dioxide as a giant covalent structure. Sodium oxide and magnesium oxide are basic in terms of acid-base character. Aluminum oxide is amphoteric, can act as an acid or a base. And then these oxides are called acidic oxides. When they dissolve in water, they form an acid. So let's look at oxides reacting with water. Sodium oxide reacting with water forms sodium hydroxide. Magnesium oxide reacting with water forms magnesium hydroxide. Lithium oxide and hydrochloric acid, of course, base plus acid makes salt plus water. Same idea here. And the oxide is basically acting as the base and accepting the H plus ions to make water. In terms of the acidic oxides, we have phosphorus oxide in a couple different forms, reacting with water to form phosphoric acid and phosphorus acid. These are acids, hence acidic oxide. Sulfur trioxide and sulfur dioxide react with water to form sulfuric acid and sulfurous acid, H2SO4 and H2SO3. Pretty simple reactions there to remember. Now the chlorine oxides may be a little bit more challenging to remember. In both cases, though, it only reacts with one water molecule, and maybe kind of just figure out, well, these are all going to be one hydrogen. They're a monoprotic acid. So what is it going to make based on everything that's over here? Well, it's going to make HClO4 if it's Cl2O7, and if it's Cl2O, it's going to make HClO. These are both acids again. Now, silicon dioxide, when it reacts with water, is no reaction because it does not dissolve. However, with a very concentrated alkali, silicon dioxide will react to form a silicate and water. Hence, silicon dioxide is considered an acidic oxide because it's reacting with a base. Aluminum oxide is amphoteric. It does not dissolve in water, does not react with water, but it can react with an acid and essentially neutralize it to form a salt in water, written as an ionic equation. Aluminum oxide can also react with sodium hydroxide in the presence of water. Gosh, I have no idea why I have aqueous water. That should be liquid. My apologies. Whew. I'm glad you caught that. So here we have aluminum oxide reacting with sodium hydroxide, and it's forming this complex ion. And this aluminum is a complex ion with aluminum surrounded by 4 hydroxides in a complex ion that's very similar to a transition metal complex ion. So these hydroxides are not available to dissolve in the water because they're part of this polyatomic ion, this complex ion. So the aluminum oxide is acting as an acid and neutralizing this base. As a TOK link, the periodic table is an excellent example of classification in science. I think excellent is almost just too simple of a word. It's more than that. How does classification and categorization help and hinder the pursuit of knowledge? This is interesting. How could classification hinder the pursuit of knowledge? Think about that one. Nature of science, looking for patterns. Of course, the periodic table is full of patterns. Connections to other topics, well, of course, the connection to acids and bases, which we're in now. Reactions and reactivity, which is connected to so many of the periodic trends that we studied within topic 2 and topic 3 already. So now, as a summary, the oxides within period 3 exhibit basic to acidic properties going across the period, and there are many reactions to place within this context. You might consider a summary statement of some sort to think about group 1 and group 17, the alkali metals and the halogens. What kind of summary can you use to remember those groups? Checkpoint question time. Checkpoint question 1, the compounds sodium oxide, aluminum oxide, and sulfur trioxide respectively are A, B, C, or D. Enter your answer and come back for a discussion. The correct answer is B, basic for sodium oxide, amphoteric for aluminum oxide, and acidic for sodium dioxide. And this is on some level memorization or remembering for sure. One more multiple choice question. Which pair would react together most vigorously? Think about the reactivity comparison of lithium and potassium and a comparison of chlorine and bromine. Enter your answer. The correct answer is C. So potassium is more reactive than lithium because when you move down in the alkali metals, you get more reactive. And in the halogens, we're comparing chlorine and bromine. And chlorine is more reactive than bromine because it is higher in the halogens. And that's our choice. And that is all. Thank you for listening. I appreciate your time on this video. Have a great day.